This is mutually exclusive and inclusive events. So when we talk about the word mutually exclusive, it's talking about something that is disjoint, something that is not being affected by another thing. Okay? So to write this down, let's write exclusive. We talked about exclusive in context of inequalities like less than or equal to and less thans. So a less than would be the exclusive. I totally misspelled that. S-I-V-E. So on less thans and greater thans, those are exclusive. They do not include the number that they're talking about. So if I said x is less than 3, it does not include the 3. Here, exclusive means that the probability of one thing, so if we said probability of A or B, it would say that when we're determining the probability of those two things in conjunction, they do not affect each other. So in order to solve something like that, we would take the probability of the first one, which is probability of A, and we just simply would add it to the second one. This is when two things don't affect each other, okay? Two things that do not affect each other, okay? Now, using this kind of, we're going to call it a formula, okay? Using this kind of formula, this is mutually exclusive events formula, if you want to write down the label. Okay, mutually exclusive events. On example 1, it will give us an example of a mutually exclusive event. It says, what is the probability of rolling either a sum of 6 or a sum of 11 of two different cubes? So let's look. It gives us a nice little chart. You would have to create this chart if you were asked this problem and you didn't get it with it. Otherwise, you could come back to this page, and there are several like this. So the question again said, what is the probability of rolling either a sum of 6, so here we go, the sum of 6's are all highlighted right here. So how many times do you see 6? 1, 2, 3, 4, 5, right? So sum of 6 happens 5 times. So the probability of it happening, or in other words, the probability of A, the first thing, or probability of rolling a 6 is really what it's telling us, right? Probability of rolling a 6 is 5 out of how many total possibilities here? Don't count them. Okay, 36, right? So 5 of 36. So that's nice. So I'm going to leave that right where it's at. And then it says the probability of rolling an 11. Is that right? Okay, how many shots are there to roll an 11? 1, 2, right? 2 of the 36. Now normally I would reduce this to 1/18 if I was going to leave my answer like that. But there's a reason I'm going to use the unreduced version. Okay. When I do the formula for probability of, notice it says or in here, of rolling a 6 or a 11. So 6 or 11. Consider these or problems. Okay. Very, very important. So when I'm considering these, I take the probability of 6, which was 5/36, and the probability of 11, which was 2/36. Okay, and I add them together. Why did I not use the reduced version of this? Right, then I would have had to have converted it right on back, right? So, because I had a common denominator, I just used it. Okay, now that I have a common denominator, that common denominator is going to stay common, and I just add the top, so I get 7/36. Can I reduce that? No. So the probability of 6 or 11 is 7/36. Simple enough? You would just add them together. Alrighty, so there's the answer for that one. Next type of probability problem we're going to start seeing is going to be called inclusive events. And this one's a lot harder just because it involves more pieces. Identifying is the biggest, probably, challenge to this. So here's inclusive. Inclusive events are joint events, okay? So these were called disjoint, as in they don't affect each other. These are called joint events because they do affect each other. Okay, they can occur both at the same time. So example 2, it says, what is the probability of rolling at least one odd number or a sum of 8 using the 2 cubes. So again, I want to look back at that chart. Okay, so here, let's go back and write down our formula. This says probability of A or B, but this time, this one will affect that one, and vice versa. Okay, so what they do is they still take the probability of the first one, and they add it to the probability of the second one. But here's the tricky part. After they do that, they then subtract the probability of them happening together, because there's an overlap. Okay, and this will make more sense here in a second. Okay, when you see it in action, you're going to go, why do we have to do all this extra work? Because you can see it. All right, so let's answer the question. It says probability of rolling a odd, or a sum of 8. Okay, so that's how I'm going to write that. The probability of rolling an odd or the sum of 8. So first of all, I need to find the probability of rolling something that's odd. I'll identify all the odd numbers. And then I need to find the probability of rolling something that is even. Or sorry, not even, that adds to 8. And then I'll look at the probability of doing both of those things at the same time, odd and 8. Okay, so I'm going back to my chart. I get her there and blow her up. So here we go. I'm going to go through here. I'm going to look at all of the odd numbers, right? So if I look at all of my odd numbers, 1s are odd, 3s are odd, 5s are odd. So I'm looking at 1, 3, and 5. So what does that tell you about every single possibility? It's going to take over how much of our chart here? How many times do you roll an odd number? So get to counting. You can use a little bit of common sense there. This might be easier if we looked. It might be easier if we looked at when are the times that there's only even numbers involved. It didn't say that both of them had to be odd, did it? It just said one of them had to be odd. So every time you roll a 1, everything in this column is included, and everything in this column is included, right? But when you roll a 2, when you roll a 2 and a 2, and a 2 and a 4, and a 2 and a 6, those are not included, right? Because those are both even. So there's 3. Then if I look at the 4s, when I roll a 4 and a 4, a 4 and a 2, and a 4 and a 6, again, that's 3 more, right? So I want to look at these different combinations and figure out when is there only even numbers involved. Okay, so go back through there and see if you can find them. I did just give you a hint, by the way. If it happens 3 times every time there's an even number involved, how many even numbers are there on a die? 3. So if it happens 3 times every time an even number is involved, how many times does it happen in total? 3 times 3 even numbers, it happens 9, right? So there's 9 times that it rolls just even and even. Just 2 even numbers. So how many then involve an odd? 27. So the probability of rolling something with an odd involved is 27 of the 36 times. And again, I could reduce that, but I'm going to add them together later, so I'm going to leave them alone. I'm going to start filling in my blanks, by the way. So 27 of 36 needs to be added to the probability of rolling an 8. So going back to our chart, I will look for 8s. There are 1, 2, 3, 4, 5. There are 5 possibilities of rolling an 8. All right? Did I miss any? No, I did not. Okay, so 5 of the 36. Say that again?
27.5.
Oh, you're already adding it up. Oh, okay, gotcha. Okay, now I'm looking at the probability of those 2 things happening at the same time. An odd number and an 8. So I'm only looking at the 8s. Okay, 2 and 6, those are both even, that doesn't count. 3 and 5, there's an odd number, so there's 1. 4 and 4, that's an even number, no count. 5 and 3, that's an odd number. 6 and 2, that's even number. So how many times does it happen that they both do it at the same time? Twice. So the probability of this one and the other one happening at the exact same time is 2. 36. Okay, so I'm going to subtract that from this total number. Because these are common denominators, this looks scary, but really all I'm doing is adding and subtracting, right? So 27 plus 5 is, say it, 32 minus 2 is 30. So we keep our common denominator common, and we get 30 over 36. All that's left to do is reduce, and I can type that into my calculator. You get 5 over 6, because I'm reducing by 6. Okay, so 5/6 is my answer for the probability of odd or 8. Because these are, I didn't even write down the word, did I? Yes, I did. Inclusive events. They affect each other. In other words, there's an overlap. Now, the way to do this without doing this whole big equation would to go through here and go, all right, every one of these that is 8 or has an odd number involved. All right, start going through here. Okay, 1 and 1. That's 1. There's an odd number involved all the way through here. 1, 2, 3, 4, 5, 6. Okay, 6. And then I would count through here. Okay, every one that involves an even number won't count. So there's only 3 in here. So 6, 7, 8, 9. Okay, then I go through each one of these and I count them all the way up. And notice that when we get to the 4 and 4, I would have to count that 8 because it's an 8, even though it's got 2 even numbers in it. Okay, when I added them all up, I would get 30. 30 over 36. So this is supposed to be a shorter way, and once you get used to it, I guess it is. But ultimately, you're adding up all of the different possibilities and subtracting when they both happen at the same time. Okay? Let's see if they got another example for us. Example 3. And this is just giving you numbers, so you just literally plug into the formula, I think, on this one. Bryson needs to randomly call 125 people from the state of Wyoming to conduct a short survey. The following data corresponds to estimated values from 2005 describing the state's populace. Bryson assumes that everyone who is employed is younger than 75. How many people can he expect to call who are either employed or are 75 years and older? So we need to determine, is this an exclusive or an inclusive event? Does one affect the other? So again, I'm going to repeat the question. How many people can he expect to call who are either employed or are 75 years or older? You think it's exclusive? One does not affect the other. Why do we know that? You just guessed. Read the last sentence. So we're going to try to get through this, guys. You were actually right, Maddie. The assumption that Bryson makes says that everyone older than 75 doesn't work, right? So the probability of calling somebody that's employed and the probability of calling someone 75 or older are disjoint. They are not going to affect each other. They are not going to affect each other because he thinks that everyone that's employed is under 75. Right? There you go. So everyone that's employed in his mind, because of this assumption that he says is under 75, these two things are disjoint. So it says how many people can he expect to call who are either employed or are 75 or older. Take a look at the population. Total population, what does that mean about the other people that are involved in this population? Because they're unemployed, right? They're unemployed and under the age of 75. Tired of bums. Maybe they're still kids. Alright, so because I decided that this was an exclusive event, that one does not affect the other, I'm going to write the probability of, let's make sure I'm answering this the way that I'm supposed to, of employed, I'm going to abbreviate that, or the age is older than 75, right? So I'm going to say greater than or equal to because I don't want to write as much. Now I'm looking for the probability of employed. I need to do that first. So to find the probability of someone that is employed, I am going to write it down as the numbers that they have given me. So what is the total number of people that are employed? 291,000. And the total people involved in that population? 510,000. So I can reduce this right away with all these zeros, right? To 291 over 510. I'm going to go ahead and do that. I could probably reduce it a little bit farther if I tried hard enough, but I'm going to leave it like that, just so I don't have to deal with those big numbers. Okay, I'm going to go ahead and write it in. 291 over 510. Now I need to find the probability of someone greater than or equal to the age of 75. So, how many people are there? 29,000. And there are, again, 510,000 people in this place. So, 29, I'm going to go ahead and reduce it. 29 over 510, so I don't have to write all those numbers. I'm going to add those two together, right? 29 over 510. Adding them together, I get 310, I do believe. No, 320. 320. 320 over 510. And again, I can reduce this again. 32 over 51. Can I reduce it any more than that? Somebody triple check me. If I can't, then I'm going to leave it just the way it is. To the answer of, oh man, I wrote all this on the wrong thing. Plus 29. Okay, so it is 32 over 51 is our answer. So the probability of being employed or greater than or equal to the age of 75 is 32 to 51 because of the assumption that he says people over 75 don't work. Otherwise, I would agree with Bailey on this one. Alright, so the next little piece says Bryson can expect 32, this is the answer, 32 out of 51 people to be employed or at least 75 years old. It says multiply the probability by the 125 people. So this is our probability right here. I'm going to take the probability and he's going to call 125 people. So I'm going to take that probability, I'm going to multiply it by my 125 and hopefully this will tell me approximately how many people that he's going to call that will fall into these two categories. Okay? Once you find your probability, you just multiply it by your total and it'll give you how much approximately you'll end up with. That's how probability works. Okay, so multiply that, 125 times 32 over 51. Give me your decimal approximation here, because I don't know what it is. Give me a decimal here. $78.431. Okay, I'll leave it at that. Now, to answer the question, it says about how many, so that tells me that I have to estimate. Am I going to tell him 78.4 people? No. You could try. It's below 5, so we'll go ahead and round it to 78, right? People, with a nice little label. So he can expect to call about 78 people who are either employed, or 75 years of age or more. Okay, so there's the answer. Any questions there before I move on? Okay. I think this is my last example. It is. Good. Let's get into it. It says Natalia has music from a variety of different artists on her MP3 player. There are 26, I'm going to write these as little reminders to myself, 26 rock, 18 pop, and 19 country, and then 10 alternative, and 7 crossover. I don't even know what that one is. Okay. That's the types of artists that she has on her MP3. The music by the crossover artists Natalie chooses is on the pop and country chart. So pop and country. So these two, yeah, there you go, some T-Swizzle. If Natalia's music player randomly selects the next artist, which is the probability that the artist will be singing a pop or country song? Pop or country. So we're looking for probability of pop or country. And we have to decide, are these events exclusive or inclusive? And we have to keep in mind this sentence. The music by the crossover artists Natalia chose is on the pop and country charts. Pop and country. So it's inclusive. Why? Because it affects one another because of these crossover artists that do both. So if I said how many pop and country and crossover artists are there, you would only add pop and country together because the crossover artists fall into both categories, right? Then I would have to subtract the amount of crossover artists there are. Alright, so let's get into this. Starting to answer the problem, it says find the total number of outcomes. Total number of outcomes, we add them together, right? So 26, somebody's going to have to help me, plus 18, plus 19, plus 10, plus 7. How much do we get? 80. Good. Next, the events are inclusive because of those crossover artists, so we're going to start finding our probability. Oops. So total is 80. I'm going to start finding the probability of first, the pop artists. So, how many pop artists are there? 18. And there are 80 total artists. So, 18 over 80, right? Then I'm going to add the probability of my country artists, which are 19 over 80. So, I have 19 over 80. Then I'm going to subtract, this is the one that's a little more difficult, the total number of pop and country artists, better known as crossover artists, right? So if I wanted to put probability of crossover, that would have been way easier. And there are 7 of those, right? 7 of 80. 7 of 80, so I'm going to subtract 7 of the 80. Then I just add these two together and I get my number. So 18 and 19 make 37. 37 minus 7 make 30. 30 over 80 I can reduce fairly quickly, 3/8. So, wait, did I do that right? Anyway, I got 3/8. Pop or country. That's interesting. Not according to the book, but according to me it is. Alright, there are a 3 of 8 chance. So the probability of these things together are 3/8. I like these better as percentages because it makes more sense to me. So if I converted this to a percent, it would be like 37.5 or something like that. Okay? It just makes more sense to me to say that there's a 37.5% chance of you getting the next person to be a pop or country artist. Any more questions before we move on?